Welcome to the video on molecules. This is the last video in the atoms, ions, and molecules section of the course. A molecule is when two or more atoms in a definite arrangement are held together by chemical forces, which we're going to learn shortly are called bonds. There are 7 elements that automatically just hook up as diatomic molecules. So they are 2 atoms of the same element that are held together and they exist as this dimer or as this diatomic molecule. And those are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. We can remember help our needy class find its brain, that acronym, or if we look at the periodic table, we can see that it really makes a nice 7. Plus hydrogen, don't forget hydrogen. There are 2 additional elements that form special molecules of itself, and that is sulfur, which typically exists as S8, and phosphorus, which will typically exist as P4. So if we were to try to figure out what's an atom, what's an element, what's a molecule, so an atom is going to be any single element, for example, oxygen by itself. That's an atom. Hydrogen is also an atom. Helium is also an atom. And lastly, we have manganese. Manganese is an atom. So those are the things that are directly from the periodic table. Now, helium is actually also an element, as is manganese. So those are elements because they exist just like that in nature. Helium is a noble gas. It doesn't need any bonding and it exists just like that. And so that's considered an element. Manganese, same thing. Manganese is a metal and it can exist on its own like that. O2 is one of the diatomic molecules that we talked about, which is also considered an element. So we can look at O2 as being an element. It's not an atom because it's 2 atoms put together. But just for clarification, O2 is also a molecule because we have a bond. So for elements, what we're talking about is how things exist in nature. And if we look, we forgot one element, and that's H2. So H2, that's how it exists in nature. But again, it's also a molecule because it has a bond. HF is a molecule. Now, this is a different kind of molecule because it actually has 2 different types of atoms put together. That's why that's not an element. That's just a molecule because it's 2 different types of atoms put together. H2O or water is going to be an example of a molecule as well. We have 2 hydrogens attached to 1 oxygen, and we have CH2O, and that is also a molecule. So I hope this exercise helps you understand the difference between atoms, elements, and molecules. Atoms are the smallest possible form of that element, and it may not actually exist in nature in that way, but this is just how we think about a single piece of that element. And in some cases, that's how it exists in nature, in which case they would also be elements. So like helium and manganese. Elements are how they exist in nature. Sometimes it's a single piece, sometimes it's 2 put together. And molecules are where we have bonds. It can be diatomic molecules like oxygen and hydrogen, or it can be different atoms that come together to form molecules with those bonds. One of my favorite things to do is to determine the molecular mass of a compound or of a molecule. So if we have 2 or more atoms held together with bonds, we can actually add up the atomic masses of each of those atoms, pull it together, and then we get what's called molecular mass. This molecular mass is the sum of the average atomic masses. And remember, the average atomic masses are what we're going to see on the periodic table. Here are a couple examples. SO2, so we have 1 sulfur molecule, and that is atomic mass of 32.065. And we multiply that by 1 because there's 1 sulfur. And we have 2 oxygens. So the atomic mass of oxygen is 15.999. We multiply that by 2, and we add that plus that, and we got 64.053 AMU, or atomic mass units, for SO2. Now, if we look at water, water has 2 hydrogens and 1 oxygen. So the atomic mass of hydrogen is 1.0079, and there's 2 of those. And the atomic mass of oxygen, again, is 15.999, and there's 1 of those. So if we do that math out, we get 18.015 AMU. Now, just a term for your reference is called a formula unit, and this is the smallest electrically neutral unit of an ionic compound. So we'll talk in a little bit about the difference between covalent bonds and ionic bonds. But in an ionic compound, what What we need is to get the formula unit. It's the smallest electrically neutral unit of that compound. It's the sum of the average atomic masses for the cations and the anions that make up the formula unit. One example is NaCl. So a formula unit would be NaCl. Even though we know that exists as a crystal with a whole bunch of NAs and a whole bunch of Cls held together in a matrix, the formula unit is the smallest possible connection of those two. So we have 1 Na, 1 Cl, 22.990 plus 35.453, and that gives us a 58.443 atomic mass units. Therefore, we can calculate the molecular mass of a molecule and the molecular mass of a formula unit. So if we want to practice, it's definitely easiest with this part of the chapter to have a periodic table close by. And if you look up the atomic mass of sodium, which actually was just on the previous page, but we'll do it again, 22.990 plus the atomic mass of chlorine is going to be 35.453, and you add those up and we got 58.443 AMU. And so that's the units that we're going to put, but that is our molecular mass for NaCl. We also just did water on the previous page, so we can skip that one. Let's go down to BaNO3(2). So barium nitrate is what's responsible for the green in fireworks. Let's take a look at this one. For barium, we have 137.328, and that is times 1 because there's only one barium. Plus, for nitrogen, we have 14.007, and we have to see how many nitrogens we have. There's 1 in this unit, but then there's actually 2 here. So that's going to be 2 times 14.007. And then if we talk about oxygen, if you remember, it was 15.999. 15.999 is the atomic mass of oxygen. And now we have to figure out how many we have. We have 3 in this unit, and then we have 2 of those. So that's a total of 6 oxygen. And so we have 6 times 15.999. If we do that math out, we end up with a molecular mass of 261.336 AMU for barium nitrate. And if I do one more example, we'll do ethanol over here. And so if we take a look, we have carbons, we have hydrogens, and we have an oxygen. And so if we start with the carbons, 12.011 atomic mass. And how many carbons do we have? 1, 2. So it's going to be 2 times 12.011. We're going to add to that for the hydrogens. And so remember, our mass for hydrogens is 1.008. And how many hydrogens do we have? We have to add those up. So we have 1, 2, 3, 4, 5, 6 total. And so that's 6 times 1008. And then, of course, we have our oxygen, which is 15.999. And in this case, we only have 1. And so if we do that math out, we end up with 46.069 AMU for ethanol. I will let you calculate glucose, aspirin, acetaminophen, and caffeine for class. Again, this is something that I think is fun and pretty straightforward. It just, again, like everything in chemistry, will take practice. So at this point, I'm going to introduce you to the idea of the mole and the idea of Avogadro's number. The mole is a basic counting unit in chemistry. The actual definition is that a mole of a substance is the amount of that substance that has the same number of atoms as exactly 12 grams of the isotope of carbon-12. And ultimately, what that becomes is the amount of any substance that contains 6.022 times 10 to the 23rd atoms, ions, molecules, particles, pieces, etc. A mole is the amount of our element that contains 6.022 times 10 to the 23rd pieces. Just like when we go to the bakery and we order a dozen, what's a dozen? A dozen is 12 pieces. Well, if we went to a bakery and ordered a mole, we would get 6.022 times 10 to the 23rd pieces. I imagine some of you are thinking, oh, this is cool. We can use this as a conversion in our dimensional analysis problem. We have 6.022 times 10 to the 23rd molecules, for example, in 1 mole. And you're exactly correct. This value which, by the way, that's Avogadro's number, 6.022 times 10 to the 23rd. That's Avogadro's number. We're going to use this primarily as a conversion in our dimensional analysis problems having to do with reactions and moles and molecules and grams, etc. So we'll learn more about that later. But here's the mole and here's Avogadro's number. A mole is 6.022 times 10 to the 23rd pieces of something, and that equals 1 mole. So within every 1 mole of water, there are 2 moles of hydrogen and 1 mole of oxygen. So if we wanted to do a dimensional analysis problem, if we are given 1 mole of water and we want to know how many moles of hydrogen, we're given moles of water and we want to know how many moles of hydrogen, we can simply do a dimensional analysis, because for every 1 mole of H2O, there are 2 moles of H because of that 2 right there. And so that gives us our answer. And I didn't write it down, but our answer is 2 moles of hydrogen. Same for ammonia. We have NH3. So if we have a mole of ammonia, we have 1 mole of nitrogen in that mole of ammonia, but we have 3 moles of hydrogen. But once it's connected, it's just 1 mole of ammonia. I hope that's clear. If we go back, we talked about molecular mass, a few slides where you add up all the pieces of a molecule to figure out the mass using the atomic weights from the periodic table. For molar mass, it's the mass in grams in 1 mole of a substance. So molar mass is the mass in grams of 1 mole of that substance. And it turns out it's exactly equal to the atomic mass units for the molecular mass that we determined earlier in this chapter. Molecular mass is the same as molar mass, is the same as AMU, is the same as grams per mole. So things to keep in mind here. Atomic mass units per molecule is the same as grams per mole. So a few minutes ago, when we calculated atomic mass units from the atomic weights on the periodic table, it's the same as saying grams per mole. So for aspirin, for example, we calculated that there was 180.2 atomic mass units, and that means that it also is 180.2 grams per mole. Now there's 6.022 times 10 to the 23rd pieces in any mole. 1 mole equals 6.022 times 10 to the 23rd pieces. We can now talk about the fact that 6.022 times 10 to the 23rd carbon atoms is equal to 1 mole of carbon atoms is equal to 12.011 grams of carbon. So those 3 things are now equal to each other, and we can use any 2 of those for a conversion factor in dimensional analysis. If we look at copper, 6.022 times 10 to the 23rd copper atoms is equal to 1 mole of copper atoms is also equal to 63.54 grams of copper. So atomic mass units equals grams per mole. Now we have these new conversion factors that are going to help us with dimensional analysis. And we can use any of these 3 for our factor conversions. So the key takeaway concepts from this slide is that the mass on the periodic table is how much 1 atom weighs in atomic mass units. If we weigh out a mass in grams that is equal to an element's atomic mass in AMU, we will always have 6.022 times 10 to the 23rd molecules. 1 mole of aspirin or carbon or copper or NaCl and water, like 1 mole of any of those molecules or compounds, have the same number of molecules, 6.022 times 10 to the 23rd, but they're going to have a very different mass and a very different volume. So here's a nice schematic of how all of the things that we're talking about here are connected. In the center, we have moles of an element and then moles of a compound. So these are going to be related using the chemical formula, right? H2O, 1 mole of water over here of the compound, and then it has 2 moles of the hydrogen. Okay, so we use the chemical formula to get from moles of a compound to moles of an element. And if we want to go back and forth between grams and moles, we're going to use the molar mass, right? So we're going to calculate the molar mass, which is grams per mole. And we can use that as a conversion factor to get us to mass or to get us to moles, whichever way we want to go. And molar mass here is big M on this figure. If we want to go to atoms, and this is going to be using Avogadro's number. So we're going to use that idea of 6.022 times 10 to the 23rd pieces in 1 mole. We can use Avogadro's number to get back and forth between moles and atoms. And on the other side, when we're talking about moles of a compound, we have the same exact scenario. We can go back and forth here using molar mass, and we can go back and forth here using Avogadro's number. So we have moles in the center, and we can go back and forth to grams using molar mass. That's calculated from the periodic table. Or we can go back and forth to atoms and or molecules and or pieces using Avogadro's number. So if we do one example here, we're going back to dimensional analysis. So this question is asking, if you have 2.75 moles of a sample of potassium, how many grams do you have? We are given 2.75 moles of potassium, and the question is asking how many grams of potassium do we have? To get from moles to grams, what conversion factor do we use? And we have to figure out what goes on the top and what goes on the bottom. So we want moles on the bottom, and then we want grams on the top. We have something that is this, grams per mole, and that is the molar mass. And the molar mass is the atomic mass units. And that, if you look on the periodic table for potassium, 39.0983. And this is moles of potassium and grams of potassium. Moles cancels, and we're left with grams, which is what we want. So if we do this math out, we end up solving for 107.5 grams, or with proper sig figs, because in our number here we have 3 sig figs. So with proper sig figs, this is going to be 108 grams of potassium. Circle it, and we are good. Now I'll do the second problem because this is going to be using Avogadro's number, so I will show you how to use that. They want to know how many sulfur atoms. So we want atoms of sulfur are there in 5.4 grams of H2S. So we are given 5.4 grams of H2S. And they want atoms of sulfur. We have to figure out how to solve this problem. So the first thing that we're going to do is we're going to look at the molar mass of H2S. So we take H 1.008 times 2 plus the molar mass of sulfur. And so we end up with 34.0808 grams of H2S in every 1 mole of H2S. Okay, so now we have moles of H2S. In order to get to atoms of S, we need to get to moles of S. We're going to put moles of H2S on the bottom, so that cancels. And we're going to put moles of S on the top. And it turns out that for every mole of H2S, there's only 1 S. So this is going to be a 1-to-1 ratio. And for a 1-to-1 ratio, you want to include that in your dimensional analysis for full credit. I need to see that you know what you're doing. So you're going to, even though this will not have any effect on the calculation, I need it in the dimensional analysis for full credit. Okay, so now we have moles of sulfur and we need atoms of sulfur. So the way that we're going to do that, we're going to divide by 1 mole of sulfur. And we know that for every 1 mole of sulfur, we have 6.022 times 10 to the 23rd atoms. That is our dimensional analysis. If we cancel our unit, we have grams of H2S, moles of H2S, moles of H2S, moles of sulfur, and we're left with atoms of sulfur, which is what we want. So if we do this math out, we end up with 9.5 times 10 to the 22nd atoms of sulfur. And so that is going to be our final answer. We were given 2 sig figs, so we have 2 sig figs in our answer. There's 2 more pages of practice problems, and you can start on these, but we'll definitely pick these up in class. There you have it. Now we know how to use the mole. We can do Avogadro's number and molar mass to do whatever we need in dimensional analysis. Good luck.